Recording in progress.
Okay, so we'll talk about some of the digital communication modes and information rate versus bandwidth, baud rate and symbol rate, some error correction techniques, and a new one they threw in of constellation diagrams. I'd never seen one before. I probably will never use one. You probably will never use one, but there's a possible test question. Okay, so it's true the digital modes, particularly things like FT8, have become very popular. I guess one of the reasons is because of the protocols they use, the fact that you can make contacts with people halfway around the world on, 5 watts, 10 watts. And it's fairly easy to use. All you need is a computer and a radio that's got a sound card in it or an adapter to go in between. Because it has such a narrow bandwidth, it's FT8 is 50 hertz wide. FT4 is even narrower, but it's not quite as good at low signal. Morse code is another one that is become more popular. We have some Morse coders in here.
One of these, yes.
One of these, yeah. Yeah, I don't think we're ready to carry on conversation. Unless we're going to be next week. But Morse code is down as 52 hertz for a typical 13 word per minute, which seems pretty fast right now. I can send a 13. I can't see. So it's in the case of the CW signal, the bandwidth is kind of a function of the keying speed and the shape factor, the rise and fall times of the signal, and talk about that in a little bit. So what's the approximate bandwidth of a 13 word per minute international Morse code transmission?
Here it is. Moms.
Shame on you. 52 hertz. Yeah, that's sending Paris 13 times a minute. That's the standard or the international word.
Oh, really? What is
Paris?
Paris? Yeah.
Yeah. Because of the number of dots and dashes in it, and spaces. What factors affect the bandwidth of a transmitted CW signal? Yeah, you wouldn't think the shape factor, but it does. Some of the other digital modes use what they call frequency shift keying. So to represent a symbol, they will actually shift frequency a small amount. In the case of like FT8, which uses audio frequency shift keying, they divide the 50 hertz bandwidth up into 8. So each 6.25 hertz is possibly another symbol state.
Another what?
A symbol state, you got, because it's there's 8 tones, so you're sending
Oh.
3 bits with each symbol, and a symbol is going to be composed of one of those 8 frequencies, and it's actually around 1500 hertz, and then that frequency shift.
I see.
It tries to keep it in the middle of the band. So you're going to have an offset depending on where you are in the 3 kilohertz band, plus that little frequency shift. Unless, of course, you do split mode, where it'll keep adjusting and keep you within 1000 to 2000 hertz offset all the time. It'll actually change your transmit frequency. Okay.
Is Brady used previous shift king too?
Is what?
RTT1?
Yeah.
Is it also using this kit? It's a two-tone thing.
I believe so. Yeah.
Is that not my? Largest, also bands.
It's let's see, market space.
Right.
And it's what? I forgot, 1200 and something. Forgot the 2 frequencies. But it's not like FT8 where they're little frequency shifts. It's 2 different frequencies. Let's see. Oh, and the bandwidth frequency, the bandwidth formula is the frequency shift times a 1.2 multiplier. I don't know where that came from. And then you add in the baud rate. Now you need to remember that because we've got about 3 questions coming up where you have to multiply and divide, or multiply and add.
David's got his,
Huh?
David's got his hand up.
Oh, okay, David.
Yeah, I'm just curious, is this the reason why the FCC was reluctant to go higher on that Pactor speed because of the bandwidth?
Yes. And they've changed it now. I think it's official, where they widened the bandwidth for some of those modes, where it used to be limited. Gosh, I think that's a test question, but I haven't reviewed that one.
It may have been 4800 baud, now it's 9600.
Something like that. But it was definitely limited because of bandwidth.
Okay, great. Thank you.
It's either in process or they've finalized that change.
I believe they
Were they-
finalized it.
So in a couple examples here, where it's a 4800 shift with the 9600 baud. If you do the little formula, you get 15 kilohertz, and the other one was like half a kilohertz. So, jeez. This mouse has got a problem. What's the bandwidth of a 4800 hertz frequency shift, 9600 baud ASCII FM transmission? You can't do that on the exam unless you write it on the back of your answer sheet before you start. And write down, divide the big one by the little.
Yes, sir. That looks.
Okay. It would seem obvious that the higher the data rate, the wider the bandwidth. So that's why there are limits on data rate because of the bandwidth limitations. So one of the things they do to try to get around that some is come up with what we call symbols, where you can have a symbol that represents 2 or 3 or even more binary bits by using some different tones. So you can keep the bandwidth fairly narrow, like in FT8, but they're sending 3 bits at a time, okay, with each one of those little frequencies. So it makes it a lot more efficient and less bandwidth used. So how can data rate be increased without increasing bandwidth?
So trying to FT8. If you're using 3 bits, you can represent 8 different values. It's zeros.
Right, right.
8 and FT8 is 3 bits.
Yes, it's because it's 8 dates. And that's why they decided to make it 50 hertz wide bandwidth. So that's why they divided by 8. So you can keep the bandwidth and have your symbol.
So FT4 only is 2 bits.
Yeah. 4 states. That's where the 4 and the 8 come from. But that's the simple part of it. It's a lot more complicated. I tried to go through the whole thing once and I got almost all the way through, but because a lot of it was developed from work they did on with submarines, underwater communications, very slow stuff, and they came up with this thing called a Costas array, which is a specific pattern that they can send, and that's embedded in FT8 at the beginning, the middle, and the end to help synchronize it, and all kinds of stuff like that. A lot of error correction on it. It's amazing stuff. In fact, the whole WSJTX suite of things are based on all the same kind of protocols. What is the bandwidth of an FT8 signal? Were you listening again?
Yes, you were.
Yes, it was what? What is?
Yeah.
I was thinking it was close to 52.
Well, they're close. Morse code is 52 and FT8 is 50, so it's better. Yeah. Except you can't really communicate much. Actually, it turns out you can embed a little bit of text in part of the protocol. But yeah, not a lot of room, but you can put some text characters in there. And of course, that depends on the guy on the other end actually replying.
Well, they have JSA call.
Right. Yeah. Use the keyboard. Okay, PSK31. It's kind of an old one, isn't it, Jack? Well, now, I don't know. One of those books said it was very popular.
It must be true.
And obviously, it gets its part of its name because it's 31 hertz wide. So it's one of the narrowest ones. And one of the things they do is they use what's called sinusoidal data pulses. Instead of looking like square waves, they kind of look like modified sine waves. I think I have a chart showing them, which helps reduce the bandwidth because you don't have any of the harmonics or anything in there that, and that's one of the issues with, we talked about earlier on Morse code with the wave shape. And you have to put some delay on the rise time, so it's more like a trapezoidal wave to keep the bandwidth narrow. Sometimes they use what's called a raised sine, where it's actually a part of a sine wave on the leading edge.
It's quite fast. Where it should be, so which we are there up, so it's cute.
Yeah. And then the other thing is doing the phase shifts, because this is phase shift keying as opposed to frequency. So you're going to change phase at a zero crossing. So that obviously, that is another thing that prevents those harmonics and spurs, keeps the bandwidth down.
How often is changing every time you get a zero across?
If it changes from a 1 to a 0 or 0 to a 1.
And
If you've got a continuous ones, then you're going to stay the same phase. When you can go to a 0, you're going to go to the other phase. So and that's for binary. I mean, you can have multiple, but in binary, it's either this phase or that phase, and that represents a 1 or 0.
so does it shift it up?
No, 90, I think.
So you come in the
Yeah, 90 degrees, because essentially you're going.
zero across, then jump 90 degrees to be
Yeah. Yeah.
Which is. $20.
Or what is?
Well, you're getting in.
well, the computer's gonna do all for you guys.
Yeah, you generate a signal, so you know where 0 is. When it's, I mean, you're not doing it, but your radio.
It's interesting because like they used to do audio. Like there's literally a key. Like if you want to talk volume, you hit C on the keyboard to find the next zero crossing. Because if you don't find the zero, it's cut there.
Oh yeah, and that's why you get key clicks on, like Morse code things.
Just wondering, like, what does the computer hear on that received signal when you don't have zero to feed instant?
Well, I think. It's a different slide. I got one in here that actually shows the phase shift waveform, and you can actually see it. This one claims to be binary phase shift keying 31, the modulation, but I don't know, it just doesn't look right to me. I don't see a phase shift. But I don't know. But it's just definitely showing the difference between ones and zeros. And the one at the top is showing instead of actually having a square wave, you're doing different rise times, and these all are what they call raised sine, where you're modifying that square wave with a sine wave to change the leading edge of it. Of course, this green one is sort of extreme, but that's also part of, it mentioned earlier that it uses sinusoidal wave shaping. That's what this is. So you're basically rounding off the edges of those pulses. So what technique minimizes the bandwidth of a PSK31 signal?
It's.
Maybe. I have to get a new mouse. What should phase shifting, why should phase shifting of a PSK signal be done at the zero crossing of the RF signal?
Probably.
Alpha? Let's see. Oh, this is talking about how symbols came about, so we could represent multiple bits with a symbol. And we talked about symbol rate, which is the same thing as baud rate or baud. And baud came from one of the early encoding things called Poe by some French guy. And instead of bit rate, we do symbol rate because it's usually multiple bits are represented by a symbol. So what is the definition of symbol rate in a digital transmission? You need Edward. I think it's a symbol changes the way, and because instead of having individual bits to it, you're having a symbol which represents multiple bits to it. So it's either a frequency change or a phase shift change. What's the relationship between symbol rate and baud? Remember, if you ever had an old analog modem, there was so many baud.
If I'm worried when the answer is simple. Because I can't be that.
The answer is simple.
Yes.
Okay, one of the things they use to encode data is called gray code. Gray code was developed so that you only have one digit change at a time. Whereas if you do a normal binary count, you can have 2 or 3 digits change state at the same time to represent the difference between a 3 and a 4, for instance. So it helps facilitate error detection because you're only expecting one bit to change in the pattern. So if you get more than that, you think it's an error. Here's a chart showing the conversion where normal binary counting up 0, 1, 2, 3, 4, up through 7. The equivalent gray code, okay, you see where 2 is now 0, 1, 1. So we only changed 1 bit. And 4 is a 6 instead of a 4. So we still only changed 1 bit. So we just reordered the representation so that you only have a 1 bit change going through the count. Now, obviously, if you change from a 0 to a 5, you got multiple bit changes. But going from 4 to 5 or 5 to 6, you still only have 1. Which digital code allows only 1 bit to change between sequential code values? Was that a too easy one too?
That was really easy, yeah, but I felt when that.
I just really like extended binary credit decimal.
You know, like the fact that
Oh, that's a real thing.
we never mentioned ASCII at all, but
I like ASCII too. I used to know the whole ASCII table. That was a long time ago.
Mm.
But A is 41 hex, I think.
like,
How does A? Oh, gee, we must have missed another one. Okay, error correction. One of the things is called the ARQ protocol, or automatic repeat request, where when the sender receives a message, if it detects errors, it can send out an ARQ back to the transmitter station to say, resend it, basically. And the number of times it can be resent is something that's usually programmed in, like a limit of 3 or 4. I mean, you don't want to sit there forever because you got a bad connection or something. So they'll usually limit it to a few tries. And then after that, you sort of have to start over. And they can also, if in some cases, they'll look for an ACK or a NAC coming back, an acknowledge or a not acknowledge, which means they didn't receive it or receive bad. So if they don't, if they get a NAC or they don't get an ACK back, they can retransmit the packet. They assume that you didn't get it properly. So how does ARQ accomplish error correction? Another form is called forward error correction, where you actually forward additional data. Sometimes it's the copies of the message multiple times. So you can do like voting, like you got to send it 3 times, and you know 2 out of 3 might be right, or other extra bits to help do error correction, like sending Hamming codes or something like that along with it, so you can correct for at least single bit errors, excuse me. And there, you don't have to retransmit, but the downside is you got to send more bits in the message in order to do that. Okay. We talk about Wi-Fi. We have a Wi-Fi expert, right? It uses called QAM, quadrature amplitude modulation, where you have 2 carriers, the same frequency but different phases. So you got like an I and Q, and then you modulate it. So essentially, you're sending the sine and cosine of the wave. So it's easier to decode it on the other end. So what is quadrature amplitude modulation? Bravo? Let's see. Oh yeah, this is the new one they threw. Where it's supposed to have fixed amplitude and phase values, so that you can help decode it. So if you have a QAM4, okay, there's 4 separate phases that you're sending. So you have 0, 90, 180, 270. And each of those is a constant or fixed amplitude. That's where this little constellation diagram comes in to represent those. And in this case, it's an 8 phase. So it's plotted on the real and imaginary axis, where Q, because it's shifted 90 degrees, is in the complex plane. It's imaginary. So each one of the states is one of these little circles around the big circle. So the and that circle is the amplitude. So you can see it for 111, it's zero phase and whatever that radius is, amplitude positive. Over here at 001, it's a negative, whatever that amplitude is. And then 010 and 100 are same amplitude, but different phases, plus and minus phase shifts. Where you use that, I don't know. Why it's in here, I don't know. It's a new question.
Right. Well, I mean, here, you look like. For example, like some applications, you would see a constellation diagram on your split. That would show you where your symbols are showing. If they're on a good clean signal, you get out of this my life memory. So if you got a good clean signal, you'll see those.
Yeah, that's true.
Very clear.
I forgot about that.
If everything's just scattered out, which signal, pull the data out.
I guess it's the app for RIDI, right? Where some of them it'll show the constellation, and when you're synced up, you'll get the circle.
Yep. You'll see the four different places. It'll just kind of pull off.
So I hadn't related that to this, but I guess that's maybe why. But they don't relate it to RIDI.
They don't get it right.
So that would have been a better example. So,
The other thing is like in some satellite communications, we'll go like if 4 is better than 2, then 8 is better than 4, 16 is better than 8. Because you're getting too many. Part of the thing is, did you guys see the movie The Martian?
see what?
The Martian, with Matt Damon.
Yeah.
Like trying to figure out how to make an alphabet. And he's like, there's 26 plus 10 numbers, 36 spots. Like, I'll never be able to tell which camera's looking at. He had to figure out another way to do it to hexadecimal. It's the same kind of thing. Like, you start bringing all your points closer together because you have more of them on the circle. The decoder or the demodulator isn't able to tell, well, is that one in this position or is it this position? Unless you have your super duper strong signals. So as you get your signals, you have to be able to differentiate, which is why if you're only using 4 symbols, it's there. Like use out of phase.
Right.
Whereas if you go to 8, like 5 degrees out of phase. If you go to 16, you're half of that.
You don't get something for nothing.
You don't get something. What's clear here? Like it's terms black or white. It's white. Galaxy. It's supposed to be. This fails. It's just easier to cleanse.
Okay, so what was the answer to this one? What does the constellation diagram describe? The acceptable states for phase and amplitude to decode. Yes. Excuse me, mesh networks. This one's still in there. I don't really see that much activity, but maybe in some places there are. I know, see the technician or general, they have more stuff about this where you modify existing commercial routers and make a mesh network by having them connect together. This is a sort of an extended of the same thing where they use the discovery and link establishment protocol in order to create the network. So, you know, contact all these other mesh stations, and then you've got a path where if any of them are down, you can find an alternate path to get from point A to point B. And they all use the regular internet protocol or an IP address as opposed to a MAC address. It's supposedly a very good choice for emergency communications. I don't know if you consider SARnet a mesh network or not. It is kind of one.
Mesh. This. However.
Yeah,
So it's.
they're connected. And I don't know if they,
If they're a mesh as in. Because it's everywhere. Yeah, now it's down this house. I don't know if it's down to.
I would think you'd have to have more than one path from each one, or otherwise you'd have a serial link and the one of them goes out, you lost the whole chain.
It's not like that. Meshes going on. Nodes and full nodes.
I think so. I think it's doing packets.
Yeah, see, traditional packet radio, which I think is. They're responsible for that, so we're trying to on. No, like, are these mesh networks they're talking about using these old Wi-Fi, programmed Wi-Fi routers?
Yeah, that, well, in the,
That you're transmitting, there's already stations. Keep moving in that area. I get what you're saying.
until it gets to the destination address.
Even APRX, distributors, distributors and IH. And pulling it through data back.
Yeah. So these stations, sort of intermediate ones, are called nodes. And you actually talk to a node, and node talks to another node. So what type of addresses do nodes have in a mesh network? An IP address. What technique do individual nodes use to form a mesh network?
Sure.
That's very easy too. It's all easy from here on out.
Yeah, it's easy. Yeah.